Chapter 4, Linear Regression with One Regressor. The superintendent of an elementary school district must decide whether to hire additional teachers, and she wants your advice. Hiring the teachers will reduce the number of students per teacher, the student-to-teacher ratio, by 2, but will increase the district's expenses. So she asks you, if she cuts class sizes by 2, what will the effect be on student performance, as measured by scores on standardized tests? Now, suppose a father tells you that his family wants to move to a town with a good school system. He's interested in a specific school district. Test scores for this district are not publicly available, but the father knows its class size based on the district's student-teacher ratio. So he asks you if he tells you the district's class size, could you predict that district's standardized test scores? These two questions are clearly related. They both pertain to the relation between class size and test scores, yet they are different. To answer the superintendent's question, you need an estimate of the causal effect of a change in one variable, the student-teacher ratio, big X, on another, test scores, big Y. To answer the father's question, you need to know how big X relates to big Y on average across school districts, so you can use this relation to predict big Y given big X in a specific district. These two questions are examples of two different types of questions that arise in econometrics. The first type of questions pertain to causal inference. Using data to estimate the effect on an outcome of interest of an intervention that changes the value of another variable. The second type of questions concern prediction, using the observed value of some variable to predict the value of another variable. This chapter introduces the linear regression model relating one variable, big X, to another, big Y. This model postulates a linear relationship between big X and big Y, just as the mean of big Y is an unknown characteristic of the population distribution of big Y. The intercept and slope of the lines relating to big X and big Y are unknown characteristics of the population joint distribution of big X and big Y. The econometric problem is to estimate the intercept and slope using a sample of data on these two variables. Like the differences in means, linear regression is a statistical procedure that can be used for causal inference for a prediction. The two uses, however, place different requirements on the data. Section 3.5 explained how a difference in mean outcomes between a treatment and a control group estimates the causal effect of the treatment when the treatment is randomly assigned in an experiment. When big X is continuous, computing differences in means no longer works because there are many values big X can take on, not just 2. If, however, we make the additional assumption that the relation between big X and big Y is linear, then if big X is randomly assigned, we can use the linear regression to estimate the causal effect on big Y of an intervention that changes big X, even if big X is not randomly assigned. However, linear regression gives us a way to predict the value of big Y given big X by modeling the conditional mean of big Y given big X as a linear function of big X. As long as the observation for which big Y is to be predicted is drawn from the same population as the data used to estimate the linear regression, the regression line provides a way to predict Y given X, big Y given big X.